Imagine like a shortcut to being truly well-informed, finding those surprising facts, getting those aha moments, but without drowning in just tons of information. That's pretty much what we're diving into today. We're taking a really deep look at this innovative agroforestry system. It's locally developed up in northwestern Ethiopia. And it's not just about improving soil fertility, which is huge, but it's also making a real dent in climate change mitigation. So our mission today, to unpack how these local farmers are using this unique mix, trees, crops, even making charcoal to turn degraded land around. We'll get into the science behind why it works so well and what it all means for sustainable farming everywhere. Let's unpack this.
It really is a fascinating case study, mostly because, well, it tackles such a big problem, both for the environment and for people's livelihoods.
Right.
See, in northwestern Ethiopia, the tradition is growing teff, just teff, a monoculture. But the issue, and it's widespread, is the soil. It's often degraded, very acidic.
Which means low yields, I imagine.
Yeah. Exactly. Insufficient crop yields. And that directly impacts the farmers, their families. They struggle. So there's this really urgent need for better ways to farm, things that are more sustainable and more productive.
That definitely sets the stage. And this is where this really clever solution comes in this teff-Acacia agroforestry. For anyone maybe new to the term, what exactly is agroforestry? Just the basics.
Sure. At its heart, agroforestry is purposefully mixing trees and shrubs right into your crop fields or animal farming systems.
Okay.
Yeah, it's about getting different parts of nature working together synergistically. The goal is to boost everything: food production, soil health, even ecological stuff like capturing carbon.
And this Ethiopian system, what makes it stand out is this very specific 4-year rotation cycle they've adopted locally, using a tree called Acacia decurrens. Could you walk us through that cycle?
Yeah, it's quite a well-thought-out sequence.
Yeah.
So year one, you're growing teff, but right alongside it, you plant these new Acacia decurrens seedlings.
Okay, intercropping.
Exactly. And here's a key detail. Unlike regular teff farming, there's no synthetic fertilizer used here. No manure either in this first phase.
Interesting. So what happens in year 2?
Year 2, they let grasses grow up next to the acacia trees. It becomes sort of a silvopasture system for that year.
Yeah.
They cut the grass, take it away, maybe sell it, maybe feed it to their livestock.
Right.
Then years 3 and 4 are all about the trees. The acacia just keep growing. No other crops, no grasses being cultivated. It's purely an acacia plantation for those 2 years.
So it builds up biomass, and then what's the finale of this 4-year thing?
That's the crucial part. End of year 4, the acacia trees are ready. They're harvested. The logs get piled up into these traditional earth mound kilns.
Earth mounds.
Yeah, covered with teff straw and soil. Then they let it smolder for about 3 to 5 days. That makes the charcoal.
Okay.
But here's the really clever bit. After they collect the main charcoal, there's debris left behind at each spot where they did the burning. About 8 kilograms of it in an area roughly 3 meters across.
And they don't just clear that away.
No, that's the point. They work that charcoal debris right back into the soil when they till it to start the next rotation. So it feeds back into the system.
That's brilliant, a closed loop. Why Acacia decurrens, though? Was there a specific reason the farmers landed on that particular tree?
Oh, definitely. It was a very strategic choice by the farmers. Acacia decurrens grows fast. You can harvest it after just 4 years, which is pretty quick for a tree.
Right, that fits the cycle.
Exactly. And it produces really high-quality charcoal. That charcoal is vital. It's energy for their homes, or, and this is important, they can sell it. It's a major alternative source of income. So it's practical, it's profitable for them.
And this is where, for me, it gets really interesting. The power of those spots where they make the charcoal. The study looked closely at the soil, right? Side eye, just the top 10 centimeters, comparing inside those charcoal spots to outside. And the differences were just huge. Soil pH, 20% higher inside. Black carbon, a staggering 164% higher.
Wow, 164%.
Yeah. Soil organic carbon, the SOC, up 48%. But listen to the nutrients. Phosphorus, up an incredible 687%.
687.
Yep. And potassium, even wilder, 788% higher. Now, they didn't see big changes in nitrogen, magnesium, sodium, or calcium right in those spots, but those other numbers, they just jump off the page. What's going on there?
It's fascinating when you break down why those numbers jump so much. The charcoal itself is key. First, it's alkaline. Its pH is around 7.9.
So it counteracts the soil acidity.
Exactly. It raises the soil pH, makes it less acidic, which most plants prefer. Second, the charcoal is packed with carbon, but it's in a very specific form, what scientists call a polycondensed aromatic structure.
Okay, sounds complex. What does that mean practically?
It basically means the carbon is incredibly stable. It's really tough for microbes to break it down. So when you add it to the soil, that carbon stays there for a very, very long time. It's long-term storage.
Ah, I see. So it's not just adding carbon, it's adding stable carbon that doesn't just disappear quickly. That's the difference.
Precisely. That structure makes it super resistant. And there's more. That acacia charcoal isn't just carbon. It's also naturally rich in some key nutrients.
Like the phosphorus and potassium.
Exactly. We're talking about roughly 38 grams of phosphorus and a massive 380 grams of potassium in every kilogram of that charcoal.
Wow.
And beyond just adding those nutrients directly, its presence in the soil actually helps the soil hold on to other nutrients better and makes them more available for plants to use. So it's both a source and helps with retention, all from what's essentially a byproduct of charcoal making.
Okay, so that's the effect right on the spots. Super localized, super intense. But let's zoom out. What about the whole field over time? Back at site eyes, same depth, comparing the whole agroforestry field to the old way, the conventional teff monocropping. There were big changes there too, right?
Absolutely. After just one rotation that's 4 years, the soil organic carbon, SOC, across the field was 112% higher than the conventional plots.
112% in 4 years.
And after the second rotation, so 8 years in, it was 169% higher. Soil, total nitrogen, also saw big jumps. 100% higher after 4 years, 131% higher after 8.
That's sustained improvement.
And it gets even more impressive if you look deeper. At Site 2, they sampled down to 100 centimeters, a full meter deep.
Okay.
After the first rotation, maybe not a huge difference in total carbon stocks compared to the teff fields, but after the second rotation, 8 years. The agroforestry plots had 159% more carbon stored in that top meter.
159% more.
And wait for it. After the third rotation, so 12 years, the SOC stocks were a remarkable 244% greater than the conventional teff fields.
244%. So what does this all mean in practical terms? Like how much carbon are we talking about?
Well, if you crunch the numbers, it works out to an apparent increase of about 21.1 metric tons of carbon per hectare per year over that 12-year period.
21 tons per hectare per year. That sounds like a lot.
How does that compare? It's huge. To give you some perspective, global studies, meta-analyses, they usually report carbon sequestration rates in agriculture, somewhere between, say, 1.4 to 2.2 tons per hectare per year.
Okay, so this is like 10 times higher.
Or more.
Ah.
Even compared to other really good agroforestry systems in sub-Saharan Africa, which might hit up to maybe 14 tons per hectare per year. This Ethiopian system is still way ahead. It's genuinely an outlier, a positive one.
So how does it do that? Why is it so effective at building up carbon and nitrogen? It can't just be the charcoal spots, right? They're too small.
No, you're right. The charcoal helps, but it's not the main driver field-wide. It's really a combination of interacting factors working together across the whole system.
Okay.
First and foremost, you have the acacia trees themselves, present for the whole 4 years. They add a lot of organic matter, leaves falling on top, roots growing and dying underneath.
Right, litter and root turnover.
Exactly. And critically, acacia decurrens is a nitrogen fixer. It has this symbiotic relationship with the bacteria, allowing it to pull nitrogen gas right out of the air and convert it into a form the plants can use in the soil.
Wow, how much nitrogen are we talking?
It can add up to 200 kilograms of nitrogen per hectare per year. That's like getting free fertilizer naturally.
Oh, it's massive. Okay, so the trees are huge. What else?
Then you've got the ground cover. The grasses in year 2, the teff in year 1, they also contribute organic matter when their residues, stems, leaves, roots decompose.
So multiple sources of organic input?
Yes. And another really big factor is reduced soil disturbance. Think about it. Conventional teff farming involves plowing the field maybe 4 times a year.
Right, intensive tillage.
In this agroforestry system, they only till in the first year when planting the teff and acacia. Years 2, 3, and 4. Minimal disturbance.
And less disturbance means?
Less soil organic matter gets exposed to the air, so less of it oxidizes and decomposes back into CO2. It helps preserve what's already there and what's being added. Plus, it significantly reduces soil erosion from wind and rain.
Makes sense. So trees adding stuff, ground cover adding stuff, less disturbance keeping stuff there, and then the charcoal spots giving those localized boosts.
That's pretty much the picture. The charcoal debris, while significant in its own spots, covering maybe 1–2% of the field, contributes that very stable black carbon and improves nutrient availability locally. But for the overall field-wide gains in SOC and nitrogen, the continuous inputs from the trees and grasses, plus the reduced tillage, are the dominant factors. It's a whole integrated system working together.
It really sounds like a holistic approach, which brings us to the big question. Why should someone listening, maybe not farming in Ethiopia, why should they care about this?
Oh, it matters hugely for several reasons. First, this system directly tackles soil degradation and acidity. It makes land more fertile, more resilient. That's a problem faced by farmers all over the world.
Sure.
Second, climate change. The amount of carbon this system pulls out of the atmosphere and stores long-term in the soil is significant. This offers a real, tangible, nature-based way to fight climate change.
So we're essentially looking at creating living carbon sinks using smart farming. That potential seems enormous if it could be scaled.
Tremendously so. And what's really inspiring here is how this came about. The study emphasizes these are locally adopted practices. This wasn't some top-down project imposing technology.
It grew from the farmers themselves.
Exactly. Which means it overcame a lot of the usual hurdles you see with, say, transferring technology to smallholder farmers in developing countries. Things like lack of resources or institutional support. This is homegrown innovation that's a powerful model for sustainable development anywhere.
Good point.
And finally, think about the farmers' lives. This isn't just about soil or carbon. By diversifying what they produce, teff for food, grass for animals, charcoal for energy or cash, the system makes them more resilient. It improves their food security and their economic situation. It's a win on multiple fronts.
Yeah, it really does sound like it. What we've seen here in northwestern Ethiopia seems like such a powerful example. This, unique multi-purpose agroforestry system. It boosts soil health, check. It provides a serious pathway for climate action via carbon storage, check. And it improves the lives of the farming communities, check. It really is a multifaceted win for the people and the planet.
It absolutely is.
But as always, with these kinds of innovations, there's always more to learn, more to fine-tune, right?
Definitely. And that brings up some important next questions. This deep dive, this study, it was fantastic, but it used what's called a space-for-time substitution.
Meaning they looked at fields of different ages side by side to estimate changes over time.
Exactly. Which is a valid approach, but imagine what more we could learn if we had actual real-time, long-term monitoring data from the same fields over many years.
Okay.
How could we optimize things even further?
Good question.
And there's another layer. We know nitrogen-fixing trees, like acacia, are great for soil fertility. But sometimes, under certain conditions, they can lead to increased emissions of nitrous oxide, which is a potent greenhouse gas.
Ah, okay. And a potential unintended consequence.
Potentially.
Yeah.
And the charcoal production itself, while creating that beneficial biochar, the actual burning process also has its own greenhouse gas footprint. So the really complex ongoing question is, how do we keep refining systems like this? How do we tweak them to ensure the net climate benefit, considering everything, the sequestration and the emissions, is truly maximized?
Right, optimizing the whole balance sheet.
Precisely. It's a complex puzzle, no doubt. But it's a puzzle with, I think, immense potential for building a genuinely more sustainable future for agriculture.